Hello friends, welcome to my channel. In this video I will cover GATE paper 2017 paper morning session thermodynamics and heat transfer part I will cover. This is part 2. The pressure ratio across a gas turbine for air specific heat at constant pressure Cp equal to 1040 joule per kg Kelvin and ratio of specific heats gamma equal to 1.4 is 10. Pressure ratio is 10. If the inlet temperature to the turbine is 1200 Kelvin and the isentropic efficiency is 0.9, the gas temperature at turbine exist is how much? So Brayton cycle, gas turbine. Cycle is like this. Pressure is constant. Pressure is constant. 1 to 2 isentropic process, then constant pressure process 2 to 3. Constant pressure heat addition 3 to 4. Work done in turbine 4 to 1 heat rejection. So here isentropic efficiency given, so this is actual condition 4 dash. So data given are Cp equal to 1040, gamma equal to 1.4, its unit is joule per kg Kelvin, inlet temperature T3 it's 1200 Kelvin and isentropic efficiency it's 0.9. So we already discussed in my previous video and in ISRO videos also already discussed pressure ratio, which is pressure P1 and here this is pressure P1, here P2. P2 and P3 both are same. P2 by P1, this is the ratio, it's 10, or P3 by P4, it's 10. So put the formula T4 by T3 equal to P4 by P3 whole to the power gamma minus 1 by gamma, or we can write it as T3 by T4 equal to P3 by P4 whole to the power gamma minus 1 by gamma. Then put the values. Data T3 is at turbine inlet temperature is 1200, pressure ratio is 10, gamma value is 1.4 minus 1 divided by 1.4. So if you solve this one, T4 at turbine exist temperature is 61.53, but this is for ideal condition. Isentropic efficiency given. From isentropic efficiency relation you will get actual turbine exist temperature T4 dash, that you have to find out. Isentropic efficiency it's T3 minus T4. If you see the graph, see T3 to T4, this is ideal, and actually T3 to 4 dash, 3 to 4 dash. So actual by ideal T3 minus T4. Put the values. Isentropic efficiency 0.9, 1200 minus T4 dash divided by 1200 minus 621.53. So from here we will get T4 dash equal to 679.38 degree Kelvin. This is our answer. 2 marks question. This is Brighton cycle TS diagram. Next question, air contains 79% of N2 and 21% of O2. On a molar basis, methane CH4 is bound with 50% excess air than required stoichiometrically. Assuming complete combustion of methane, the molar percentage of N2 in the products is how much? So, air into nitrogen 79%, oxygen O2 21%. Methane is burning. So with 50% excess air, CH4 plus air, if it will burn, you will get water plus CO2 plus N2. CH4 plus 2 into air contains O2 plus N2. That percentage also given on molar basis. So 79 by 21 N2, you will get 280O plus CO2 plus 2 into 79 by 21 N2. For balancing, we are multiplying. So 50% excess air, so 1.5 times excess air. 1.5 times of 2, you will get 2 into 1.5, 3 O2 plus 79 by 21 N2. Here you will get 280O plus CO2 plus 3 into 79 by 21 N2 plus O2. Then N2% in molar basis, N2% is equal to 3 into 79 by 21, total is 2 water, CO2 1, then O2 1 plus 3 into 79 by 21. So if you solve this one, you will get 73.85%. This is the answer. 2 marks question. Only equation, chemical equation you have to solve. Next question, from heat transfer, radiation heat transfer, two black surfaces A and B, AB and BC of length 5 meter and 6 meter respectively are oriented as shown. Both surfaces extend infinity into the third dimension. Given that view factor F12 is 0.5, T1 equal to 800 Kelvin, T2 equal to 600 Kelvin, T surrounding is 300 Kelvin, and Stefan Boltzmann constant sigma given 5.67 into 10 to the power minus 8 watt per meter square Kelvin. This unit also important, so many times asked in other examination. The heat transfer rate from surface 2 to the surrounding environment, how much? In kilowatt. Let surrounding is 3, surface 1 and surface 2. So AB given 5 meter, BC equal to 6 meter. Then F12 given 0.5, T1 it's 800 Kelvin, T2 equal to 600 Kelvin. T surrounding or T3 equal to 300 Kelvin. Stefan Boltzmann constant given. So A1, take width as 1 meter, unit width. A1, surface 1, A1, area is BC, area of BC equal to 6 into 1, 6 meter square, and A2, area of AB is 5 into 1, 5 meter square. So F11 equal to 0, F22 also 0, flat surface. So F12 plus F11 plus F13 equal to 1, it should 1. F11 is 0, F12 given, so F13 equal to 1 minus F12 is 0.5. So you will get 0.5. F13 equal to 0.5. Then reciprocity relation you use here. A1 into F12 equal to A2 into F21. So from here F21 is A1 by A2 into F12. F12 already we got. F12 given 0.5. So 6 by 5, A1 is 6 meter square, A2 is 5 meter square, F12 here 0.5. So final answer you will get 0.6. F21 equal to 0.6. So again for body 2 or surface 2 you apply F21 plus F22 plus F23 equal to 1. F22 is 0, F21 is 0.6, so F23 equal to 1 minus 0.6. Its value is 0.4. F23 we got, and heat transfer from surface 2 to surrounding is 3, we take as 3. Q2 to 3 we have to find out. Q2 to 3 formula is surface 2 to surrounding. Surrounding is 3. A2 into F23 into sigma into T2 to the power 4 minus T3 to the power 4. Put the values. A2 is 5 into 1. F21 we already got 0.4 into sigma value 5.67 divided by 10 to the power 8, or you can multiply 10 to the power minus 8 into T2 600 to the power 4 minus surrounding temperature 300 to the power 4. If you solve this one, you will get 13778.1. This is in watt. So in kilowatt, 13.77 kilowatt. In question something is wrong, so they gave marks to all. In IIT also they are giving wrong question. So for this question they gave mark to all persons. Heat is generated uniformly in a long solid cylindrical rod diameter 10 mm at the rate of 4 into 10 to the power 7 watt per meter cube. The thermal conductivity of the rod material is 25 watt per meter Kelvin. Under steady state condition, the temperature difference between the center and the surface of the rod is how much? This question is little bit difficult and time taking also. That formula, cylindrical rod formula, you have to use heat conduction for cylindrical rod. So data given, D equal to 10 mm. From here radius equal to R equal to 5 mm, or in meter 0.005 meter. Then heat generated, Q gen 4 into 10 to the power 7 watt per meter cube. Thermal conductivity K is 5 watt per meter Kelvin. Temperature difference we have to find out. So heat conduction equation in a long cylinder. This is also very important for ISRO examination, ISRO and IS. They are asking directly that equation, 1 by R into K T by dr plus Q generation rho C. So this is for heat conduction equation in a long cylinder. For constant thermal conductivity K, constant K, you will get 1 by R equal to D by dr R plus Q generation by K equal to rho C by K. Here steady state given, K by rho C is alpha, thermal diffusivity, R into plus 1 by alpha. So here steady state, so this term is 0, only 1 by R by K equal to 0. Multiply R, Q generation into R by K equal to 0. Let this is equation 1. Integrate equation 1, then we will get R dt by dr equal to by K, here R square by 2 equal to C1. C1 is integrating constant, divide R to R by 2 equal to C1 by 2. This is equation 2. Then again integrate, you will get T equal to T plus into R square by 2, 2 into 2, 4, 2, here it's C1 by R, so C1 into 1 by r dr ln r you will get plus C2. This is equation 3. These are two equations, 2 and 3. Then substitute boundary conditions. Substitute boundary condition in equation 2. You will get at r equal to 0, here at middle or at center dt by dr equal to 0, surface temperature, this is Ts, here it's TO. So at r equal to 0, dt by r equal to 0. So if you to put this boundary condition in equation 2, you will get 0 plus Qg into 0 divided by 2k equal to C1 by 0. So C1 equal to 0. And our equation 3 is Qg r square divided by 4k C1 ln r plus C2. C1 value we got 0. So T plus Qg r square by 4k equal to C2. Then again substitute r equal to 0, at center t equal to T0. So TO plus 0 equal to C1 is 0. So C1 into ln r is 0 plus C2. So C2 equal to TO. So C2 value if you put here, that this is equation 4. C2 value put in equation 4, you will get T plus Qg r square by 4k equal to TO. This is equation 5. Then again substitute r equal to Rho for outer surface, its value equal to 5. In meter term we have to write 0.005 meter. T surface temperature is Ts in equation 5. So T equal to Ts Qg Rho square divided by 4k equal to TO. Then put the values. Ts plus Q generation, heat generation is 4 into 10 to the power 7 into Rho is 0.005 square divided by 4 into thermal conductivity is 25 equal to TO. So TO minus Ts equal to 10 degrees Celsius. If you solve this one, you will get this answer. 2 marks question. Little bit lengthy, direct formula. Thank you friends. Thank you for watching my video. Thank you.